Hello and welcome to our second lesson for the GCSE Unit 1 for Chemistry, looking at changing states. So today we're really trying to answer this question: why do different substances have different boiling points? You can see three examples there. Water, the most common compound we talk about, and you would need to know, the exam board would expect somebody to know that water boils at exactly 100 degrees Celsius. Oxygen, on the other hand, we tend to think of oxygen as a gas because in the temperature that we live at, oxygen is already boiled, it's already a gas. But if we could reduce the temperature down to minus 183 degrees, it would actually turn into a liquid. At the other side of the scale, we have iron. Now, unfortunately, the picture shows liquid iron, which is not very helpful because we're talking about boiling, which is becoming a gas. So iron would melt around about 880 degrees, don't quote me on that, but it would actually turn into a gas. You could get gaseous iron if you had 2862 degrees Celsius. But the question is why? Why do some elements and compounds and substances have such low boiling points, and why do some other substances have such high boiling points? And that is the question we're trying to answer today. So I cannot emphasize enough how important this concept is for the rest of your GCSE chemistry. This concept is going to come up time and time again when we talk about ionic bonds and covalent bonds and intermolecular forces and fractional distillation. They love this question, and if you understand it, this answer appears everywhere in your curriculum. So learn it now. So blue box, the amount of energy needed to change a state, so either from a solid to a liquid or a liquid to a gas, or vice versa, depends on the strength of the forces between the particles of a substance. So we're talking about the forces between particles. So here we have two examples here. Now I've gone for something very simple. There's all sorts of reasons why the forces would be stronger or weaker, but you can see here, the two particles are bigger. And because they're bigger, there is going to be a stronger attractive force between them. That's just basic science. And B here, the particles are smaller, and so they have a weaker attractive force. That makes sense, doesn't it? So the reason will depend on all sorts of things, the type of particles you've got, whether it's a molecule, whether it's an element, the type of bond that's holding them together, the structure of the substance. All these things will affect how strong these forces are between the particles, and therefore how much energy you would need to take to break them. But the general idea, guys, is that the stronger the force, or the stronger the bond, and you go into more detail whether you would use bond or force later on, but the stronger this attraction between the particles, the more energy, the more heat energy you need to break them, and therefore the higher the melting point and the higher the boiling point. So just looking at this diagram again, this point here, this change of state here, the melting point, is the tipping point when the solid had enough energy, those particles have been given enough heat energy to overcome enough attractive forces to start behaving differently and therefore become a liquid. Now remember, if we were reducing the temperature, that would also be the point where the liquid particles no longer have enough energy, so they start acting like a solid. So that's also a freezing point. It'd be the same temperature in any substance, in any given substance. So for water, it's 0 degrees. For iron, it would be a different temperature. And this point here then, okay, that tipping point, the change in state when the liquid particles have enough energy to start breaking away from each other, to overcome those attractive forces and start behaving differently and become a gas. And that is your boiling point. Alternatively, if we were cooling it down and we were removing the energy, it's the temperature at which that gas starts to behave. Those particles don't have enough energy to behave like a gas anymore, and so they start behaving like a liquid, and it's that tipping point between the two. So if we were going to look at a particular substance specifically, we're going to look at water. That tipping point, that point where the solid particles have enough energy to behave like a liquid, is going to be 0 degrees. That's melting point or freezing point. That's your tipping point there, the change in state, the temperature at which it changes state between solid and liquid. You would be expected to know that. And the boiling point then you would need to recognise as 100 degrees Celsius. That, again, at that point where the liquids have got enough energy to start behaving like a gas, or if we're going the other way, where the gas no longer has enough energy to behave like a gas and therefore starts behaving like a liquid again. Alternatively, if we change it to a different substance such as iron, now obviously you are used to iron being a solid, and that is because it doesn't melt, it doesn't behave like a liquid, it doesn't have enough energy to behave like a liquid until 1538 degrees. So that's a lot higher. I thought it was about 800, so sorry. 1538 degrees Celsius. And then again, if it was going to have enough energy to become a gas, you would need 2863 degrees Celsius. So you can tell there, those bonds or the attractive forces between the iron particles are much, much, much stronger than the attractive forces between the water molecules. And that's why it has higher melting points and higher boiling points. So if we look at a common non-metal such as chlorine, very different behaviour. What do you think about the bonds here, guys? So if I'm telling you it melts at minus 101 degrees Celsius and it boils at minus 35 degrees Celsius, what does that tell you about the bonds or the attractive forces between those particles? Well, hopefully you would recognise that that they're very weak, that it doesn't take a lot of energy, a lot of heat energy to break these attractive forces to get chlorine to behave, have enough energy to behave like a gas. And so these are weak attractive forces between these particles, and that's why it has such low melting points and boiling points. So again, I'm not expecting you to do this progress check. I just wanted to show you the sort of questions I was asking in class. But look at those core concepts, the sort of things that you're writing down, that's on a flashcard, that's easy to remember, that sums up everything I've said in the last 7 minutes. Adding energy overcomes attractive forces. Okay, you might even add in heat energy or adding thermal energy overcomes attractive forces. The stronger the attractive forces between particles, the more energy is needed to break them. And those two core ideas there summarize everything we've just been saying. Okay, so let's look at a question then that you might get in an exam situation. I suggest to get the most out of this, you pause the video, you write down your answers, and then you come back and have a look at how I've done it. So here are the boiling ranges for petrol and diesel, and I have a table of results here. Now, whenever you see a table in an exam question, you're going to use it, okay? So don't ignore it. I have some fractions. I have petrol and diesel. I have an approximate boiling range. So there's a range of temperatures here that they boil at, and I've got a number of carbons. The question says, how do the sizes of molecules in petrol and diesel differ? How are the sizes of the molecules different? Okay, well, nowhere on the table does it say size of molecules. So it's either talking about the boiling range or it's talking about the number of carbons. Which one's the most logical there for size of molecule? It's probably going to be the number of carbons, isn't it? The number of carbon atoms, that's going to change the size of the molecule, isn't it? Okay, so I'm looking at this data here, number of carbons. And it says, how do the size of molecules in petrol and diesel differ? Well, petrol has got 5 to 10 carbons in it, and diesel has got 13 to 17 carbons in it. Okay, that's carbon atoms. So what would I say for my answer? Well, I might say there's less carbons in petrol, or I might say there's more carbons in diesel. I might say, because it's asking about the size of molecules, I might say the molecule in petrol is smaller, the molecules in diesel are bigger, something like that. Well, let's see what the mark scheme says. So the mark scheme wanted that the molecules in petrol are smaller than those in diesel, or ORA, which basically means the other way around. You might have said the molecules in diesel are bigger than those in petrol. It also allows the idea that the molecule is smaller, or in brackets it says number there. So if you quoted that you've said there's less carbon, that you would be able to accept that. They've also used the word shorter here. You wouldn't necessarily know what that means though at this point in time. Or you could say fewer carbons. Okay, or the other way around. So you would say there's more carbons in diesel, or diesel is bigger, or there's more. It's longer. Okay. So the next question then says, explain why the boiling range for petrol is different from the boiling range of diesel. So I'm going to notice that I've got a command word there, explain. Whenever you see explain, it means give a reason. So you're looking for the scientific reason for something. Well, what am I trying to explain? What am I trying to give a reason for? Right, I'm trying to explain why the boiling range for petrol, and if I look at that table, the boiling range for petrol is between 30 and 80, is different from the boiling range for diesel, which is between 205 and 290. Right, so the question is, why does petrol have a lower boiling range than the diesel? And this comes back to that core concept, doesn't it? It's something to do with the attractive forces. It's something to do with the energy needed to break those attractive forces or the bonds. The exam scheme, sorry, that's very small there. It's actually worth 3 marks for this one. Did you mention that you've got intermolecular forces between them? So again, I've mentioned intermolecular, but not really. So at this point, if you're just coming across this in year 9, if you'd said forces at this point, you'd be fine. Did you mention that they're weaker or smaller in petrol, and therefore there's less energy needed to overcome those forces, and therefore linking it with the fact that it boils at a lower temperature? In which case you've done very well. If you'd simply said petrol boils at a lower temperature or has a lower boiling range, you would still pick up 1 mark. You can get that with no understanding whatsoever. You're just reading that off the table. What did they allow? They allowed bonds rather than forces. They ignored any reference to the fact it doesn't boil at a high temperature, because that's not the point. You're saying why are they different? So you'd have to talk about higher or lower, stronger or weaker, more energy or less energy, because it's a comparison, petrol to diesel. So this is a sort of question that they might give you when they want to talk about changes of states and understanding that different substances have got different boiling points, different melting points. They don't give you a diagram, but for myself, I find it difficult to actually work with this without a diagram. So for me, I would be jotting down at least these lines to help me. So let's have a look at this question. It says, what state would substance X be at room temperature if its boiling point is 340 degrees Celsius and its melting point is 30 degrees Celsius? So first of all, it's worth recognizing that room temperature in chemistry is 20 degrees, unless they say otherwise. Okay, so we're talking about what state would substance X be at 20 degrees. So let's put some numbers in here. It says the boiling point is 340 degrees. So let's put that there. That's the boiling point between liquid and gas. And its melting point between solid and liquid is 30 degrees. Okay. So where is 20? If I think of that as a number line, where is 20 on this number line? Up here. Well, if I start over, it's over here somewhere, isn't it? I haven't quite got to 30 degrees. We're over here. And so I'm still in the solid area. And so substance X at room temperature 20 degrees would still be a solid. So I use these number lines to help me, because my brain just doesn't like it any other way. Okay, so if you're feeling confident, pause the video and have a go at these. Just jot down your answers. If it helps to draw that number line, do so. I know I would be. Okay, so again, room temperature 20 degrees unless stated otherwise. So substance W, right, so on this number line, 20 degrees, let me get my little pointer thing, 20 degrees, that's minus 18, so I'm going to be past here, but I'm not going to go past here. So it's melted, so it's a liquid, but it's not yet boiled, so it's a liquid, isn't it? Okay, liquid, lovely. So for substance X, it melts at 150. Where's 20 degrees on that number line? Well, it's way back here, isn't it? So it's not even melted yet, so it must be a solid. Okay. This one here, minus 190, minus 84. So plus 20 is all the way over here somewhere, isn't it? And so it's already boiled, so it's already a gas. Okay, and then this one here, minus 56, 16. Where's 20 there? It's just after this, isn't it? So it has boiled, but only just. Okay, so that's boiled, so it's already a gas. Okay, so you can see there, hopefully, me showing you how I've worked that out. Okay, that, guys, is the end of this lesson. I hope that's been helpful. See you later.